Hello everyone, so let's look at how we can use unsupervised calibration to tackle high-dimensional stochastic calculus and the future of rough volatility. So let's start by addressing the elephant in the room, the mathematical roadblocks we face today. So first is the curse of dimensionality. Traditional PDE methods rely on spatial grids, meaning as we scale up to dozens or hundreds of assets, the computational cost explodes exponentially. Second, we face the rough volatility barrier. Financial markets simply aren't Markovian. Modern models use fractional Brownian motion, which strips the system of its semi-martingale structure and renders classical Feynman-Kac equations completely unusable. In short, we cannot compute backward pricing equations using classical grids when the market moves forward in such complex ways. This brings us to the core dichotomy of quantitative finance, the forward versus the backward stochastic differential equations, or SDE. Nature and observable markets move forward in time from today to maturity, anchored by a known initial state. Evaluation, however, moves in the exact opposite way. It propagates backward from maturity back to today, anchored by strict terminal contract payoff. To put it simply, nature moves forward, valuation moves backward. So, let's look at the forward path. Think of this as marching into uncertainty. We start at time zero with the known asset price, and as time progresses, random market shocks push the asset through observable market progressions until it reaches an uncertain future state at maturity. The backward path operates in the reverse order. It anchors firmly to reality at maturity, which is the strict terminal payoff of the contract, and propagates backward against the flow of time to find our ultimate destination, the value of the derivative today. So, what exactly are we looking for? Let's break down the anatomy of this valuation into two key variables, V0 and Z0. V0 or Y0 is the initial condition of the BSDE. Financially, this is the holy grail. It represents the exact fair price of the derivative today. Then we have ZT, the spatial gradient. So financially, ZT is our continuous hedging strategy, often known as delta. It dictates the precise portfolio rebalancing required to perfectly offset market noise. Next, absorbing the shock. So you can think of ZT as a dynamic risk mitigation dial. It is not passive. If the market experiences a sudden shock or jump, ZT tells us exactly how much the underlying asset we must hold to replicate the portfolio and absorb the specific shock, ensuring the discounted price remains a martingale. So this leaves us with the massive computational paradox. To price the derivative, we must work backward from the terminal payoff. But the state variables determining that payoff, like rough volatility and the underlying asset, match forward from time zero. In a non-Markovian environment, how do we compute this backward equation when the state is stubbornly moving forward? The answer is that what we call the algorithmic flip. We reframe the backward problem entirely into a forward learning task. We do this by treating the unknown initial price V0 and the hedging strategies ZT as trainable neural network parameters. So the result, both the market state and our valuation can now march forward in time. So here is how that forward would look like. At any given discrete time step, We take the current market state and feed it to the network. Then the network predicts our hedge or ZT, then add our deterministic drift, and crucially multiply by our predicted hedge by the true market shock. This gives us our next state, YT plus 1. So the neural compass, instead of trying to find one massive global function to solve the whole equation, we deploy sequential sub-networks at each discrete time step. The neural network essentially acts as our compass, constantly adjusting the hedging portfolio as we march forward blindly into the simulated future. Now, this entire architecture relies on a critical synchronization, the shared increment mechanism. Think of the market path as the valuation path as two interlocking gears. If the market gear rotates by a specific random shock, the valuation gear must receive the exact same torque. The Euler-March locks these equations together by feeding the exact same simulated Brownian increments into both the state generator and the neural network hedge. So, why sharing increments is essential? It's because the market and valuation paths are hit by different random shocks. So the gears decouple. Financially, this means our neural network evaluates the wrong reality. It attempts to hedge against a market move that didn't actually happen. So mathematically, it causes a total failure. The terminal loss function becomes completely meaningless because our final price prediction no longer corresponds to the specific simulated path of the underlying asset. So when perfectly synced, we can simulate thousands of forward paths, tunneling them until they all crash into the terminal payoff wall. The distance between our predicted final value and the true payoff is our terminal misfit. Using unsupervised learning, the network backpropagates this misfit, adjusting our initial guess V0 and our hedge ZT until the paths perfectly land on the true payoff, requiring absolutely zero labeled training data. So this isn't just an empirical trick, it carries strict theoretical guarantees, because according to the theorem, the mean squared error between the model implied option prices and the true market prices is uniformly bounded by our loss function and the discretization error. This means parameter estimation accuracy and option price discrepancies are mathematically controlled. So we can deconstruct our total pricing error into three visible blocks: the inherent time step error from our Euler scheme, our terminal misfit, optimization loss, and the payoff approximation error. The takeaway here is powerful. If we shrink the time step and minimize neural networks loss, the total pricing error fundamentally must collapse. So theoretically, it guarantees in practice that we can actually drive this terminal misfit to zero, because thanks to the universal approximation theorem, the loss can be minimized to an arbitrary degree. This guarantee rests purely on two pillars: the intrinsic market fitting capacity of our chosen model and the universal approximation capability of our neural network size and depth. So, this causes a massive paradigm shift into how we handle calibration, because traditional supervised methods require generating massive synthetic training datasets. By training this as an unsupervised deep BSDE problem, we completely eliminate that primary computational bottleneck. So by escaping this, We can do things we previously thought that they were impossible when applied to complex models like the rough Bergomi on historical S&P 500 data. We can model parameters as time-varying functions rather than flat scalars, resulting in highly stable calibration and extremely competitive error rates. So finally, we shatter the dimensionality barrier entirely, where traditional methods fail past 3 or 4 dimensions. The Deep BSDE method successfully solves nonlinear pricing equations with default risk across 100 underlying assets simultaneously, converging rapidly to the true fair price in just a few minutes. So, to conclude, by treating financial valuation as an unsupervised deep learning problem, we have successfully bridged the gap between forward market mechanics and backward derivatives pricing. It brings elegance by eliminating massive data generation, rigor through bounded theoretical errors, and unprecedented scale, and effortlessly handling 100 plus dimensions. So now the curse of dimensionality has been broken, and the timeline has been bridged.